Welcome to AI Paper Podcasts. This is where we give you those rapid, thorough updates you need on the cutting edge of machine learning research.
Yep, keeping you right up to speed.
Today, we're diving into, well, a really persistent problem, attention scaling. Specifically, how do you build an LLM that can handle truly massive context lengths without, needing infinite memory?
It's probably the central architectural bottleneck right now. For you, the technical professional listening, the problem really boils down to the KV cache.
Right, that working memory in standard transformers.
Exactly, and it just expands linearly with sequence length. So you get this nasty OS growth in compute and memory costs for every single token.
Which means once you start talking about context of, say, 100,000, 200,000 tokens.
Forget about it. The cost just becomes completely unsustainable for training, let alone deployment.
Okay, so the researchers behind this paper, this Swax paper, they tackled this head on. They came up with a new hybrid design.
Yeah.
But, and this is the kicker, they paired it with a training insight that's, well, feels completely counterintuitive.
It really does challenge some assumptions.
So, if you just need the absolute essentials, maybe for a quick update, here are the key insights in under 60 seconds. Ready?
Let's do it. 1 minute key insights summary start. First up, the architecture. This paper introduces Swax. It's a hybrid model, but critically, it only uses components that have a fixed memory state. So it combines fixed size sliding window attention, or SWA, layers with xLSTM specifically, the linear recurrent neural network layers from xLSTM. The result: a model with a fixed constant compute cost per token. Doesn't matter how long the input sequence gets. Second, the really surprising finding. For fixed window sizes, they actually found that making the sliding window larger actively hurt the model's ability to recall information from long contexts. Yeah, using the longest window they tested, 2048 tokens, basically led to near zero accuracy on long context retrieval tasks like Ruler 980. But shorter windows, like 128 tokens, they forced the xLSTM part, the long-term memory component, to actually train properly and specialize. Third, the solution. How do you get the best of both worlds? You need that precision from long windows for short tasks, but you need the long-term memory too. They came up with stochastic window size training. Basically, during pre-training, they randomly alternate between a short window, like 128, and a long one, like 2048. And finally, the result. Swax models trained this stochastic way. They outperformed all the fixed window versions. They did better on short context reasoning benchmarks and on the long context retrieval tasks. And this held up even at the 7 billion parameter scale. 1 minute key insights summary end.
Okay, that sets the stage perfectly. So our mission today is to really unpack how this fixed state memory powerhouse works, and maybe more importantly, why this specific training process seems to be the key.
Right. If we just look at the basic resource problem, standard softmax attention, SA, it's incredibly effective, right? State-of-the-art results.
Sure. It's precise.
Very precise. That exponential feature map minimizes interference between keys, which is why we get such good retrieval and reasoning accuracy from transformers. But like you said, that KV cache growth, it just makes massive in-context learning impossible because of the cost.
So if the standard transformer approach hits this kind of scaling wall, what's the architectural path the authors took to guarantee that constant memory usage?
They made a hard pivot. They decided to only use components designed from the ground up for fixed state computation. So on one side, you've got linear RNNs.
Right, like LSTMs, or in this case, xLSTM.
Exactly, specifically the xLSTM framework. These things maintain their crucial hidden state. Think of it as HT and ZT in constant memory. It doesn't grow with the sequence length.
Which gives them that unbounded reasoning capability, right?
Yeah.
An O1 cost per token, no hard token limit.
Precisely. But historically, there's always been a trade-off, hasn't there?
Yeah. Recall, RNNs are great at processing sequences step by step, but pulling out specific facts from way back, often not as good as transformers.
Absolutely. Pure recallability tends to be inferior. So the Swax hybrid design is trying to get around this unbounded memory versus high precision problem. They combine two different fixed state mechanisms.
Okay, so what are the two components?
For the linear RNN side, they use the MLSTM cell, that's from the xLSTM family. And they chose it specifically because its multiplicative gaping mechanism is apparently much better at handling signal mixing and nonlinearities compared to standard LSTMs. So potentially better recall than older RNNs.
Interesting. And they pair that with sliding window attention, SWA. Let's define that clearly.
Yeah, SWA is super important here. It completely replaces the standard global self-attention. Instead of looking at every single previous token, it restricts the attention mechanism to only look at the previous W tokens. That's the sliding window.
So it's a local view.
Exactly, a strictly local view. By limiting the receptive field like that, the complexity just plummets. It goes from being dependent on the whole sequence length, OS, down to just being dependent on the window size, OW, per token. Much cheaper.
And they use rope E within that window too, rotary positional embeddings.
Yep, standard practice for local attention models. It helps encode the relative positions within that small window.
Okay, so we've got these two pieces. A local high-precision softmax attention thing, SWA, and then this global, unbounded, but maybe less precise, linear or recurrent thing, xLSTM. How do they actually stick them together in the model?
They went for a really simple approach, actually, interlayer hybridization. They just alternate SWA layers and MLSTM layers one after the other in a 1-to-1 ratio.
Ah, okay. So layer 1 might be SWA, layer 2 MLSTM, layer 3 SWA, and so on.
Exactly. And the idea is that this elegantly splits the work. The SWA layers handle the high-fidelity, super precise local reasoning stuff where the dependencies are recent, within that window.
And the xLSTM path.
That path, with its global view, gets tasked with maintaining a compressed working memory. It handles the long-term knowledge propagating state across the entire sequence.
Right, now we get to the really interesting part. The paradox. This seems to be the main sort of intellectual contribution here. When they started playing with fixed sliding window sizes, trying out 128, 256, 512, going up to 2048.
The assumption, based on pretty much all prior work and metrics like validation perplexity, was that bigger windows would always be better. Right.
Makes sense. More context should lead to better predictions.
And initially, for short context tasks, that's exactly what they saw. If you looked at their results, the Swax model with the biggest fixed window, Swax.2048, had the best validation PPL. It also performed strongest on standard short context reasoning benchmarks, things like Human Eval Plus for code generation or MBPP.
Okay, so far so good. Checks out. But you mentioned earlier this sharp drop-off when they looked at length generalization.
Exactly, complete reversal. When they switched to evaluating long context retrieval, specifically using the ruler needle in a haystack, or NIAH, benchmark, the results just flipped entirely.
Flipped out.
The Silepio TAC 2048 model, the one that was best on short tasks, it became the absolute worst performer on long context. On sequences reaching 65,000 tokens, or even 131,000 tokens, its recall accuracy just cratered. It went down towards 0%.
Wait, hang on. So giving the model a longer attention window, which you'd think gives it more local information to work with, that actually undermined its ability to remember things from far back in the sequence?
Yes, that's the core finding. It seems totally backwards, doesn't it?
It really does. So how did the shorter windows do?
That's the other side of the paradox. The Slepstrax models with much shorter windows, 128, 256, 512, they maintain significantly better long context performance. The Slax .128 variant was hitting around 30% recall accuracy, even out at 131,000 tokens.
Wow. So the long window didn't just fail to help, it actively destroyed the long context performance.
Pretty much, yeah. It actively degraded it.
Okay, so what's the hypothesis here? Why does this happen? How do they explain this? Because it really goes against intuition.
Their hypothesis boils down to something like, undertraining, or maybe lazy reliance is a better term. Think about the two memory paths the model has.
The SWA path and the xLSTM path.
Right. The SWA path is super precise, but only local. It's like having access to a perfect answer key, but only for the last few pages. The xLSTM path is the global one, the long-term memory. It's like a compressed notebook covering everything, but maybe the notes are a bit harder to read, less precise.
Okay, I think I see where you're going with this.
When the SWA window is really long, say 2048 tokens, almost every dependency the model needs during its pre-training local grammar, maybe a reference from a few hundred tokens ago, it falls within that precise SWA window.
So the model learns to just use the easy, accurate path.
Exactly. It's the path of least resistance. The model becomes computationally lazy. It learns to rely almost entirely on the more precise softmax attention in the SWA layers for handling pretty much everything it sees during training.
And the consequences.
The global linear attention layers, the xLSTM components, which are the only part of the architecture structurally capable of true, unbounded long-term memory, they basically get ignored. They're neglected. They're undertrained for their specific job. They never really learn how to properly compress information and recall it over those very long ranges.
That's fascinating, because the flip side is, if you use a short window, like 128,
then the model is effectively blinded to most mid to long range dependencies through that SWA path. It has to learn to route information that falls outside that tiny window to the only component left that can possibly handle it.
Which is the global constant state xLSTM.
Precisely. It forces the xLSTM layers to specialize in long-term modeling, which leads to much better length extrapolation when you test it on really long sequences.
Did they have any evidence to back this up?
Yeah, they did. They showed results in the appendix, I believe, where they trained a model that was just SWA with a 2048 window, no xLSTM at all. And guess what? It performed almost identically poorly on the long context tasks as the Swax 2048 hybrid.
Ah, okay, so that confirms the hybrid model with the long window was basically just acting like the SWA-only model, essentially ignoring the xLSTM part.
Seems like it. It confirms that reliance on the SWA when the window is long.
This really changes how you have to think about optimizing context windows, doesn't it? Yeah. It's not just about compute versus how much context you can fit. It's actually a critical training hyperparameter that dictates how different parts of your model specialize.
Exactly. You need the long window's precision for good performance on short tasks at test time, but you actually need the short window during training to force the long-term memory component, the xLSTM here, to learn its job properly.
So that's the challenge then. How do you get both? How do you retain that large window performance for short tasks, but ensure the xLSTM gets trained for the long haul?
That's where the stochastic window size training comes in. It's the proposed solution.
Okay, how does that work exactly?
The method itself is actually pretty elegant. During pre-training, for each batch of data, they simply alternate the sliding window size stochastically. They define two sizes. A large one for test time performance, which they set at 2048, and a small one for regularization and specialization, which they set at 128.
So on some training steps, it uses the 2048 window, and on others, it uses the 128 window.
Yep, randomly chosen per batch. The probability of choosing the small 128 token window varied a bit depending on the model size.
Oh, how so?
For their smaller 1.4 billion parameter models, they used a probability of p0.5 for the small window. So roughly half the training steps used the short window, half used the long one. Kind of an equal balance between forcing specialization and training for local precision.
And for the bigger models?
For the larger 7 billion parameter models, they actually increased the pressure. They boosted the probability of sampling the short 128 token window up to p0.75.
Interesting. So 3/4 of the time, the big model was forced to use the short window.
Right. Which suggests that maybe larger models with more capacity are even more prone to becoming lazy and relying on that local SWA path. So they need a stronger push, more forceful regularization to make sure the xLSTM component gets properly trained.
That makes sense. It's like you're intermittently applying a kind of structural dropout, aren't you? You're temporarily disabling the effectiveness of the long-range view within the SWA mechanism.
That's a great analogy. It really is like Dropout, but applied to the attention window size itself. But they added one more crucial step to this process.
Oh, what was that?
Annealing. They realized that the Swax 0.128 model, the one trained only with the short window, while it was great at long-term retrieval, it actually performed relatively poorly on the short context reasoning tasks.
Right, because its local view was always limited during training.
Exactly. So they knew they needed a way to kind of recover or polish that short context high-precision performance right at the end.
So how did the annealing work?
It was pretty simple. For the final 10% of the total training tokens, they just stopped the stochastic sampling. They switched off the small window entirely and fixed the window size back to the large 2048 size for all remaining steps.
Like a final fine-tuning phase, just using the target test time window size.
Precisely. It acts as a final polish, maximizing the performance on those short context, high-precision tasks right before you finish training, but hopefully without undoing the long-term generalization ability that the earlier stochastic phase built up.
Okay, so the crucial question then.
Yeah.
Did it work? Let's look at the performance of this final stochastically trained model. It had to be good at both short and long context tasks simultaneously.
And it seems like it did. Looking at their results tables, the stochastic model achieved comparable, sometimes even slightly superior, short context performance compared to the best fixed long window model, the Swax 0.2048. That includes validation PPL and those reasoning benchmarks.
So the annealing step definitely worked. It recovered that local reasoning capability.
Looks like it, yeah. And then, crucially, what about the long context stuff, the whole reason for this complex training?
Right. How did it do on ruler NIH?
It performed on par with, or in some cases even slightly better than, the best fixed short window variant, the Swax .128. It maintained that robust recall on the needle in a haystack tasks way out to 131,000 tokens. And critically, it drastically outperformed the fixed Swax .2048 model, the one that got lazy.
And this held true across different model sizes.
Yep, consistent results reported for both the 1.4 billion and the 7 billion parameter scales.
Okay, so what really stands out here, the main takeaway for me, is that the poor length generalization people might see in these kinds of hybrid fixed state architectures might not be an inherent flaw in using a long attention window.
Exactly. It seems to be strictly a training issue. It's a consequence of the model learning to over-rely on a local, highly precise mechanism when it's available.
It's a fundamental lesson, really. If your model has access to a very effective but locally limited tool, like SWA with a long window, your training strategy must actively force it to also learn how to use its globally capable, even if perhaps less precise, tool like xLSTM.
Well put. The stochastic window size here is the mechanism that forces the xLSTM to specialize and learn its role.
And that brings us back to that dropout analogy you made earlier, stochastically shrinking the window.
Yeah.
It really is conceptually similar to traditional dropout, isn't it?
I think so. You're intermittently disabling or weakening the best or easiest path, the wide, precise SWA, specifically to force the model to build robustness and generalize using the other available mechanism, the xLSTM.
It's like architectural regularization driven by the training schedule.
Exactly. And the practical implication here, especially for you listening, maybe you're an ML engineer, this is potentially huge. The Swax architecture offers an alternative path that gives you fixed compute costs and constant memory usage per token.
Which is the dream for scaling.
Right. And they've shown that by using a smarter training strategy, not just relying on the architecture alone, you can successfully combine the local precision you get from softmax attention with the unbounded memory of something like xLSTM. The result is highly competitive performance without that KV cache scaling nightmare.
So Swax really underscores that success in building these massive long context models isn't just about novel architectures. It's maybe even more about finding clever training strategies that leverage constraints to enforce specialization.
Absolutely. It's about making the model learn how to use all its parts effectively.
Which leads to a really interesting final thought.
What?
Well, you framed this stochastic window training as a kind of attention dropout.
Right.
Applied to a specific structural component, the window size.
Yeah.
So it makes you wonder, what other structural components inside these modern fixed-state LLMs, maybe parts of the recurrent mechanisms, or specific gating functions within the xLSTM cells, or even connections between layers could you potentially target with similar stochastic masking or disabling during training?
That's a great question. Could you force other kinds of specialization? Could you improve generalization even further, maybe to different data types or sequence lengths by strategically, stochastically weakening certain pathways during training?
Exactly. What other forms of architectural dropout might unlock better performance or generalization? That's definitely something to mull over.
It really is. Where else can we apply this principle of train with constraints to perform without them? That feels like the next horizon.
A fantastic thought to end on. Thanks for breaking down this fascinating paper with us today on AI Paper Podcasts.
My pleasure. Always interesting to see these clever training tricks emerge.